Video is going to be regarding section 3.3, which deals with a lot of the converses of some of the parallel line relationships that we talked about over the last couple days. So I'm going to start with a warm-up here. We're going to start by initially talking about the converse of the corresponding angles theorem. So what I'd like for you to do is to just think a little bit about what the converse is, go back and look at what the corresponding angles theorem is, the one that we studied in section 3.2, and then I'd like for you to, without looking at ahead in your book or anything, just see if you can come up with what the converse of that theorem would say. Go ahead and sketch a diagram, make sure you label it, and then based on your diagram, go ahead and write a given and a proof statement for this theorem as if we were going to prove it. Then we'll talk about the proof here in a little bit. So go ahead and hit pause. Please do this because I think I'm trying to give you a sense of what this would be like in class, to get notes in class, and then kind of use open up some of our class time to just get a little bit more time to work on some problems in class together. So please hit pause at this point and go ahead and fill out this sheet. Okay, so we're going to go ahead and take a look at the answers to these, kind of one at a time here. So first of all, we'll just go ahead and state the theorem. And I have it kind of typed out here for everybody. So if two lines and a transversal form corresponding angles that are congruent. Okay, so now we're saying, again, the converse, we're saying that the corresponding angles are congruent, then the lines are parallel. Okay, so we're using corresponding angles and the fact that they're congruent to show that the lines are parallel. We'll sketch a diagram to show what that looks like. So I just kind of drew a generic diagram here. Lines L and M. And I've labeled angles 1 and 2. And notice when I labeled those angles 1 and 2, I actually drew the congruent symbols in. This guy and this guy, the little arc here, that's our visual representation of congruent angles, so we can keep track of stuff on the picture. And then based on that, our given and proof statements would look something like this. So, we have a representative sample there. 1 and 2 are a set of corresponding angles. So what we would be given is that angle 1 is congruent to angle 2, and then what we would try to prove is that L is parallel to M. And again, the idea is that we're always, in trying to prove a theorem, we're always given the hypothesis of the statement. Here we have a picture, and we're given that the corresponding angles are congruent. And what we're trying to prove is the conclusion of that statement. We're trying to make the conclusion that those two lines are parallel. So here's what the proof looks like. Well, forget it. This proof is actually going to be delayed for a few chapters. We're going to have to do this in a slightly different way than what we have done so far. Okay, and I don't necessarily like to do it this way, but this is the way that our book has chosen to do it, and that's fine. So right now we're just going to accept it as if it were a postulate. So we're going to say, we're just going to say that this actually is true for now. We can call it either a postulate or a theorem. I guess at this point we're going to probably just assume that it's true, but the book calls it a theorem because in Chapter 5 we will actually come back to this and prove it. So they're kind of staying consistent, I think, with what that is in terms of just looking at the theorem itself, as being provable using other stuff. So we're going to call it a theorem. I think the book calls it a theorem, so we'll try to stay consistent with that verbiage as well. Okay, so let's move on to the next slide then. We'll look at the converses of some of the other ones. So we'll start with the converse of the alternate interior angles theorem. And so we'll state that. Think of maybe initially about what the alternate interior angles theorem says. That if you have parallel lines, then the alternate interior angles are congruent. So ours will be just the converse of that. So we're going to look at it like this. If two lines and a transversal form alternate interior angles, that are congruent. Okay, that's the important part. We have to get that congruence in there. Okay, so now we're saying that the alternate interior angles are congruent. Then we say that the lines are parallel. go ahead and just sketch a quick diagram of what this thing is going to look like. So we'll have something like lines L and M. And the given information is going to be that angle 1 is congruent to angle 2. One of those sets of alternate interior angles is actually going to be congruent. So based on that diagram, then we're going to go ahead and write the given and the proof statements. Again, the hypothesis of the statement is essentially that L and M are parallel to each other. And what we would like to be able to prove out of that, what we need to be able to prove out of this, is that angle 1 is congruent to angle 2. Notice that we're talking about congruence here. We're not saying that the measures of the angles are equal. And of course that's true, but we would need another step to make that conclusion. So right now we're just sticking with congruence. So that's the way we would set it up for this guy. And then, so we are going to prove this one. Okay, we can prove it using the theorem / postulate that we just talked about, that converse of the corresponding angles theorem. So we're going to start with a pretty quick 2-column proof for this guy. And again, we'll maybe use that kind of that same picture that we had before. So of course the given information is that angle 1 is congruent to angle 2, and that's our given. That's the hypothesis of that converse theorem. So what we're going to need to get to do, think about what we have to work with here, right? We have the corresponding angles theorem to kind of work with. Again, we've kind of assumed that to be true. Again, the book calls it a theorem, but we're going to go ahead and use that. But we have to, of course, if we're going to use it, then we have to have some level of corresponding angles to work with. And so, we could put this a variety of places, but let's put it up here. We're going to call that angle 3. And, pretty much based off of that, then we have to say that angle 1 is congruent to angle 3. And, of course, that's because of our vertical angles theorem. If two angles are vertical angles, then they are congruent. Again, vertical angles is one of the things that we can assume from a picture, so we don't have to necessarily define that as being vertical angles first. We can pull that from the picture. Okay, and then pretty much, what we have from there is you can probably see from these two that, since 1 is congruent to both of those, that angle 2 is congruent to angle 3. By putting these two steps together, and we can call that our transitive property of congruence. And then at that point, we're pretty much good, because what we have just shown, right, is that these two are congruent to each other. 2 and 3 are congruent to each other, and of course, if that's true, those are in fact corresponding angles. And since they're congruent, which we have just shown in step 3, then we can say that the lines are parallel because of the converse of the corresponding angles theorem. So our conclusion here is that L is parallel to M, and justification corresponding angles converse theorem. Which again essentially says if corresponding angles are congruent, then the lines are parallel. Okay, so that's our basic 2-column proof for this. We're going to turn this into I think actually we're going to sort of skip this a little bit. The next slide says to write it as a paragraph proof, and we've done quite probably enough of that. Then I'm going to let that one go. I would, at this point, if you want to practice that, you're welcome to, but essentially just kind of explaining everything that we did step by step. But in a little bit more narrative of a style. And we'll get some more practice with paragraph proofs over the next couple of weeks too. But I also wanted to make sure that we took a look at what a flow proof was. And that's one of the 4 main types of proof that we've not yet talked about. So we've done 2-column, and we definitely talked about paragraph proofs. So the basic idea here is that we're going to turn this thing into an alternate representation. And flow proof is probably one of my I probably prefer this one to a 2-column proof because I feel it does a better job of showing the connections between the statements, and I mean, quite literally, I think it flows a little bit better than the 2-column proof. So essentially here you can kind of pick this up from what we have here. So we're gonna essentially write all the statements that we have in boxes, and then underneath those boxes we're going to put the justifications or the reasons, and then we're going to show how things are connected. Okay, so probably better to do this through an example. So we're going to use the same picture as we had before, and maybe I'll just redraw this real quickly. So here we have L and we have M. We have the same basic structure as what we had last time. We're going to use this other angle 3 over here to help us with the proof. All right, so we know we have to prove. Our goal is to prove that the 2 lines are parallel. And so basically what we do here, and this is a really simple one. It's only 4 steps, which we already saw. But the idea is we're going to put angle 1 is congruent to angle 2. We're going to put that in a box, and the reason for that goes right underneath the box. Okay, angle 1 is congruent to angle 2. That's given. And so at that point, we need to sort of put the other pieces of our proof into place here. The next part that we said was that angle 2 is congruent to angle 3, and that's because of the vertical angles theorem. Okay, and there's no connection between those two. Those are pretty independent statements. However, the next one is not. The next one, we have a third statement that's a consequence of these two. If I know that that 1 and 2 are congruent in the first box and the one below it, and that 2 is congruent to 3 by the vertical angles theorem, then we can put those two ideas together. Okay, and again, this is why I kind of like this, because it actually shows the flow of logic a little bit better. And what we can say is that angle 1 is congruent to angle 3, and of course that's our transitive property of congruence. And then, of course, once we know that 1 is congruent to 3, then our last step, and again, that flows directly from knowing that 1 and 3 are congruent to each other, we can say that L is parallel to M because, again, of the converse of the corresponding angles theorem. Okay. Again, knowing that the corresponding angles are congruent will tell us now that those lines L and M are parallel, and that's really what we're going for. Okay, so that's the basic idea of a flow proof, and we'll see some of these that are pretty complicated, some that are pretty easy like this. We'll do an example here in just a couple minutes. So let's go on to the next slide here. And I should have mentioned earlier, if you have any questions, along the way here, things that you didn't understand what I said or you weren't sure what I was talking about, please make sure you mark those in your notes and put like a little star or highlight it or something so that you can ask those questions, on our next day of class. That's how we'll start off our next class. Is I'll just ask if anybody had any questions from the video or there are parts you didn't understand. So make sure that you mark those down so that you can answer those questions. There are a couple others, and of course the other 2 theorems have converses as well. The other theorems that we talked about in 3.2. So we essentially have something like this, and this is kind of the basic idea. Again, we have L and M here. If I have angle 1 and angle 2 here, and if I know that they're supplementary, so if angle, let's write that out as a symbol instead. If angle 1 and angle 2 are supplementary, then of course L is parallel to M. Okay. And so that, of course, is the converse of our same side interior angles theorem, which essentially gave it to us the other way. Okay, now I do want to talk a little bit about that. Our book, I think, is really sloppy on this particular theorem, and the original as well. The book says, if 1 and 2 are supplementary, they kind of interchange the measure of angle 1 plus the measure of angle 2 is equal to 180, which is technically not correct. So what we want to say there is that if we know that they're supplementary, Okay, so maybe if this were in a proof, we would probably want to say at some point above this that the measure of angle 1 plus the measure of angle 2 was equal to 180. That means that they're supplementary by definition of supplementary angles. And then once we've established that they're supplementary, then we could say that the lines are parallel. Okay, so I'm going to kind of slightly tweak what the book is doing with that, because I thought in chapter 2 they were really specific about making sure that you defined it as supplementary first, and then saying, as a result of the definition, that the measures of the angle sum to 180, and then they got kind of sloppy with it in this chapter. I'm not really sure why, but we're going to stay kind of consistent with the way that we did stuff in the previous chapter, chapter 2. So, anyways, this is the same side interior angles converse theorem. Of course, this can be proven too, but you'll be doing that either in class or in homework, maybe or over our next class. But that can be proven as well. And then we have another one that goes along with our alternate exterior angles theorem. So we also have this one. It's just the converse of alternate exterior angles. So something like this. Again, knowing that these two are parallel, or not parallel, but knowing that those two are congruent to each other. If angle 1 is congruent to angle 2, then L is parallel to M, and this is our alternate exterior angles converse theorem. It's important that you put the converse in, right? Because that is kind of the idea. We know the relationships of the angles. That tells us that the lines are parallel and not the other way around, as we talked about in the last section rather. Okay, so those are two. I have one more that I'd like to kind of work on together, and then I'm going to let you tear yourself away from the video screen here. So let's see. So this one, we're given that angle 1 and angle 3 are supplementary, and we're trying to prove that A is parallel to B. And what I want to do with this one is actually do a flow proof with it, just to kind of show you some further examples. And there are some examples in this section of the book as well, but maybe we do as well to maybe do at least one more of these as example. So in here, we're essentially going to start that angle 1 and angle 3 are supplementary. That's our given information. Again, we put the reason or the justification underneath the box. Okay, and it's helpful oftentimes for us to kind of have a sense of where we're going with this thing, right? So at some point, we're gonna, knowing that, then we're gonna kind of know essentially that these two lines are parallel, that A and B are parallel. And so I guess there's a couple different ways that we could probably approach this. But at some point, we have to get one of those previous theorems that we've just talked about kind of involved in this guy, because our ultimate result is that we have some parallel lines here. So you may notice that they have sort of this other angle 3 kind of going in here, right? And so what we note is that angle 1 and angle 3 are supplementary. That's given. But we also know some relationships about angle 1 and angle 2. And so I think what we ought to be able to do there is to say something that angle 1 and angle 2 are supplementary as well. But remember our flow of logic when we do that. So angle 1 and angle 2 form a linear pair. Okay, and we've talked about a couple different ways of actually saying that. It was one of the assumptions that we can make from our pictures that they're a linear pair. It's based off of the definition. So our reason is that is the definition of linear pair. And then, of course, kind of our knee-jerk reaction to that is once we know that they're a linear pair, then we can say that angles 1 and angle 2 are supplementary. All right, so angle 1 and angle 2 are supplementary, and that comes from our linear pair postulate. Remember, that says that if two lines form a linear pair, then they are supplementary. So we're really just really exactly using that postulate in that case. So, we could do one of two things here. We could then kind of convert all these, and you might sort of start going to that just out of habit. We might next, kind of get the measures of the angles equal to 180 and whatnot. But we don't have to do that in this one because we really want to get to, and sometimes it helps to kind of work these kind of things backwards. Move this guy out of the way. Think about where we need to head to this, right? We need to eventually get to the idea that A is parallel to B. And so, what we want to probably think about here is we need to get some sort of angle congruences in, okay? So if we convert these two statements, this statement and this statement, if we convert those to equality using the definition of supplementary angles, then I have to do some things in equality and then convert it all back to congruence. And I could go that route, but one of the theorems that we talked about in the last section, but the last chapter is really, really, really helpful here. And when you can know that it's helpful to use it is when you have two different sets of angles. So here I have angle 1 and angle 3 being compared, and in this other step, so 1 and 3 is being compared here, and 1 and 2 are being compared here. And so what we can note there, and this is not like a substitution step, it's not like a transitivity kind of thing, but we had this congruent supplements theorem back in the last chapter that we actually proved in class. That was our second big theorem that we proved, the congruent supplements theorem. And that essentially said that if you have two angles that are congruent to the same angle, let's try that one more time. If you have two angles that are supplementary to the same angle, then they themselves are congruent. And so let's look at what we have going on here. We essentially have that angle 1 and angle 3 are supplementary, and we have angle 1 and angle 2 are supplementary. So both 2 and 3 are supplementary to the same angle. So we can invoke that theorem and say, well, that tells us that 2 and 3 have to be congruent. And so that's what we're going to do here. We're going to say that angle 2 is congruent to angle 3. And we can put in that, this idea that's the congruent supplements theorem, or we can just actually kind of articulate what that actually means. We can say that if you forget the names, then usually what we'll do for some of the ones that may have special names we might not remember is you can just kind of verbalize what that relationship is. So here I might say angles that are supplementary to the same angle are congruent to each other. Okay, so angles supplementary to the same angle are congruent. And then actually, if you go back and look at the Chapter 2 theorem sheet, that's theorem 2.2. And again, I don't ever want you to have to memorize those numbers because those are kind of arbitrary designations as to what's 2.2 and 2.3 and all that. So you can either call that the congruent supplements theorem or just kind of explain what logic you use to get that. So the only thing that's missing here really is that comes from these two steps. It comes from knowing that 1 and 3 are supplementary, and it also comes from knowing that 1 and 2 are supplementary. And so by showing those lines, it really is saying putting those two steps together give us that 2 is congruent to 3, which is why I like it maybe just ever so slightly more than the 2-column proof, because it just kind of shows that logic a little bit more clearly. Okay, hey, so we're almost done here. And so this guy here then takes me to this, because once I know that 2 and 3 are congruent, then that's my converse of the corresponding angles theorem again. Okay, and so converse of the corresponding angles theorem. And of course, may have forgotten to put this on the last one, but we definitely want to put that at the end just because it's cool. All right, so that's all I have for this set of notes. We're going to do that other example, this next example. Don't worry about doing that. It's a little bit more complex of a proof, and we're going to work on that in class over, maybe not next class, but the following class. I think we're going to get to this, but I wanted you to have it on a piece of paper so that I didn't have to make another copy somewhere. Okay? All right, so thanks for watching, and have a good night.